In Calculus 2, at the end of the semester, we did parametric curves, like curves that were given by parametric equations, where your x-coordinate was a function of t and your y-coordinate was a function of t. We called t the parameter, and t was free to be whatever kind of real number it wanted to be. Now, if we're talking about 3D space, both x, y, and z coordinates are all going to be a function of t, my parameter. And so t can be any real number, and then x, y, and z have to be a function of t. So if we're talking about a line, then the parametric equation for a line is going to look something like this. So x, y, and z are linear functions of t. And in this setup, this line is going to pass through the point x naught, y naught, z naught. And where you see these little a, b, and c coefficients, your line is going to be parallel to this vector, right? Your line is going to be parallel to the vector ABC. In other words, you can think of your line, if you have the point x naught, y naught, z naught somewhere in space, then your line is just the set of all points where you start from this point and then you move any multiple of a vector, right? So t is that multiple, and then a, b, c is the vector, right? And so that gives you the set of all points that are parallel to that vector, and that ends up making a line through space.
It is like a representation of a transformation
Yeah.
of vector a.
Mm-hmm. So this next definition, the definition of symmetric equations for a line, this is what I mean by symmetric equations for a line. What it takes to go from sort of this parametric equation over to the symmetric equation is we say, well, my x-coordinate is given by x naught plus at. If you just take this equation and you rearrange it a little bit to solve for t, solving for t would give me x minus x naught over a. I can do the same thing for y, because we know my y coordinate is given by y naught plus bt. So now if I solve for t, t is equal to y minus y naught over b. And I can do the same thing for z. So my z coordinate is given by z naught plus ct. And if I solve for t, it would be z minus z naught over c. So now all I have to do is say t equals t equals t. And then that's how I get x minus x naught over a is equal to y minus y naught over b is equal to z minus z naught over c. But this is what we call the symmetric equations for a line. And you can always do that as long as a, b, and c are not 0. If like b is 0, then you can't really do this because you can't divide by 0. You could still give the parametric equations for that line, you just couldn't do this symmetric equations thing. Okay. So here's an example. Find the parametric and symmetric equations of the line that passes through the point 0, -2, 3, and is parallel to this vector v. So in the parametric side, we need my equations to look like x naught plus at comma, y naught plus bt, comma, z naught plus ct. And since my line is going to be parallel to this vector is going to be my vector with a, b, c as the entries. And of course, since this point belongs to my line, this point can be my coordinates x naught, y naught, z naught. So I'm finally ready to write my parametric equations for this line, and I can write 0 plus 1t negative 2 plus 3t 3 plus 5t. And that would be the parametric equations for this line. And then the symmetric, again, is just sort of remembering that formula, and then we just plug stuff in. So we say x minus 0 over 1 equals y minus negative 2 over 3. And that's equal to z minus 3 over 5. Or you could just write x equals y plus 2 over 3 equals z minus 3 over 5. So one thing I encourage you to do if you're working through, oops, not that. If you're working through homework problems at home and you have your laptop or whatever ready, go to GeoGebra.com. Start calculator, and then you have to switch it from graphing to 3D calculator. And then you can type in exactly what we just typed in. So we can do t comma negative 2 plus 3t comma 3 plus 5t. And so sure enough, that was the parametric equations for my line in space. And so you can see that line going through my 3D space here. And just to check our work, what we would do is we would try to plug in this point next, 0, negative 2, 3. And sure enough, that point is on the line. And yeah, I keep clicking the wrong one. It should also be parallel to the vector 1, 3, 5. But I don't know how this works, so I don't know how to plot a vector. Does that work? No. That doesn't work. Maybe square brackets. No, that doesn't work. Okay, never mind. Okay, new example. Find the parametric equations of the line that passes through these 2 points. And so in this case, I've got like a point over here and a point over here in 3D space. And how do I find the line that goes between them? What we're going to do is we're going to name this point A, and we're going to name this point B. And what I know is that my line must be parallel to a vector that stretches from A to B. Right? So if the tail of the vector is at A and the tip of the vector is at B, my line needs to be parallel to that vector. And so this vector from A to B is going to be the coordinates of B minus the coordinates of A. So that'd be like 3 minus negative 2, 1 minus 1, and 5 minus 0. So this vector is going to be 1, 0, 5. And since my line must be parallel to this vector is sort of like my vector with entries ABC. Ah, you're right. Thank you for catching that. Yeah, so 3 minus negative 2 is 5. Now, I know my A, B, and C. I can actually choose either one of these. And it doesn't matter which one you choose. But one of these is going to have to be my point with coordinates x0, y0, z0. And it's really up to you which one we want to use. Let's go ahead and use B, just for kicks. And so my parametric equations are going to be 3 plus 5t, comma, 1 plus 0t, comma, 5 plus 5t. Okay. So here's a lot. So I say, suppose you are given a point and a vector that live in three-dimensional space. There's only going to be one unique plane that both contains that point and the plane is orthogonal to the vector that you're given. So I'm going to try to get some implements here. It's okay. So this is my plane in 3D space, right? This is my vector. What it means for a vector to be orthogonal to a plane is that it sort of makes a 90-degree angle with the plane in every direction, right? So this marker is orthogonal to the plane as long as I'm holding the base of it flat against the whiteboard. Right? So this vector is not orthogonal to the plane anymore. That one is. Okay, so if I tell you a specific point in space that has to belong to this plane, and I give you this vector and I say, your plane has to be orthogonal to this vector and pass through this point, the only possibility is that your plane has to be that plane. So that's what I'm saying with this first theorem here.
So you have to finalize the plane?
Yeah. I'll show you how to do that.
Because any point we choose on that plane, so the vector formed by the known point and another point x, y, and z, that vector and the normal are always perpendicular. So if we do the dot product, it's going to be 0.
Yeah. Okay. So if you want the standard equation for a plane in 3D space, this is what we call the standard equation. There's a standard equation, or a standard form equation, and a general form equation. But the standard form is going to be this, which is important to have in your notes. And whenever you write this equation, the plane that's described by that equation is always going to include the point x naught, y naught, z naught. If you do just a little bit of algebra to this equation, you can rearrange it to look like this. If you do that, then this lowercase d is just going to be negative a x naught plus b y naught plus c z naught. But d would just be a scalar, right? I mean, it's just a number. Then this is what we call the general form equation for a plane. So if you have a vector that's orthogonal to a plane, that's what we call a normal vector. And that's not really unique, right? The direction is unique, because in order for me to have a vector that's orthogonal to this plane, it can only be pointed in one direction. But what's not unique is the length, right? You could have a normal vector that's really short or a normal vector that's really long. You know, the magnitude of that normal vector is not unique. So any vector that's orthogonal to a plane is what we call a normal vector. And this is a little bit tricky as far as vocabulary goes, because a normal vector is not the same thing as a normalized vector. Okay? let me say that again. Whenever we say the normal vector, this means orthogonal to a certain plane. But this is not the same thing as normalized, because normalized means it's a unit vector. You can have a unit normal vector, which you could call a normalized normal vector. But not, just saying the word normal vector does not imply that it's normalized. Yeah, it's just how it is. Okay.
So a normal vector to the xy plane would be the k.
K.
And then for
And yeah, in fact, k would be a normalized normal vector to the xy plane. It would be the unit normal vector to the xy plane. Okay, so in these two equations, whether you have it in the standard form equation for the plane or the general form equation for the plane, if you have a vector that's a normal vector to the plane, meaning it's orthogonal to the plane, then I'm just a little bit imprecise right here when I say this, but if your vector is normal to the plane, then it has to be a scalar multiple. So this is actually not super precise, but it has to be a scalar multiple of the coefficients a, b, c, right? So lowercase n is representing a normal vector to your plane. Okay.
So is any vector that is parallel to a normal vector, is a normal.
Yeah. Okay, and then the last thing I have to say down here is that any 3 points in space will define a plane as long as they're not all collinear, right? If all your points lie in the same line, then you could have infinitely many planes that pass through that line. But if you just are given 3 points in space, there's only one plane that passes through all 3 of those points. Okay. So I know that was a whole lot. Here's an example of how we might use all this new knowledge. It says find the general form equation of the plane containing these 3 points. So the general form equation is going to look like ax plus by plus cz plus d equals 0. That's what we want to find, but we just need to know what is a, b, c, and d. Now I know that since I'm given 3 points, that these points uniquely define a plane. But in order to determine that plane, what I need is 1 point in the plane, and that's already given to us. I just have to choose one of these to be my x0, y0, z0 point that belongs to the plane. That can be any one of these. The other thing I need is a normal vector. So how we're going to find a normal vector is this. We're going to say this is my point A, this is my point B, this is my point C, just giving them names. We're going to find the vector that stretches from A to B, and we're going to find the vector that stretches from B to C. And those vectors, since A, B, and C are all in the plane, those vectors should also lie in the plane. Now, how do I find a vector that's normal to the plane?
Maybe cross B.
The cross product, yeah. So the cross product of AB and BC has to be orthogonal to both AB and BC. So if it's orthogonal to these 2 vectors that lie in the plane, then it's going to be normal to the plane itself. So this is my strategy for finding me a normal vector. Now AB is going to be the vector that I get from just subtracting the coordinates of B minus A. So I'll have 1 minus 1 is 0, 4 minus 2 is 2, and 1 minus 3 is negative 2. Now I'm going to cross that with BC, which is going to be the coordinates of C minus the coordinates of B, and that will be negative 2 minus 1, negative 1 minus 4, and 0 minus 1. And that will be the determinant of this matrix. And that will be I times the determinant of this matrix minus J times the determinant of this matrix plus K times the determinant of this matrix. So that will be I times negative 2 minus 10, negative 12. And then this is 0 minus 6. And this is 0 minus negative 6. So this is going to be the vector negative 12, positive 6, positive 6. There we go. And remember, what we were just finding is a normal vector. We know that this vector is normal to my plane. So using the formulas we had before, this vector is going to have entries that we can call lowercase a, b, and c. And then we can use these a, b, and c as negative 12, 6, 6 whenever we go back up here and plug those in to my general form equation. So I have negative 12x plus 6y plus 6z. And then I have to find what d is equal to 0. I'm going to go ahead and select my one point in the plane to be A, which tells me that x naught is 1, y naught is 2, z naught is 3. And in order to find lowercase d, I might have to start with the standard form equation and then just manipulate it into the general form, right? And so let me go ahead and write the standard form equation as well. So in standard form, the equation is a times x minus x naught plus b times y minus y naught plus c times z minus z naught.
Wouldn't j be negative?
What is negative?
The j, the letter j from the matrix.
You're saying why is there a negative here?
No, wouldn't it be negative because it's positive states and then it's not negative states inside the parentheses. Negative 3 times negative 2 is 6.
So this is 0 times negative 1 is 0 minus positive 6. Yeah, 0 minus positive 6. Yeah, there's a lot of minus signs to keep up with. There's like 4 minus signs in a row, so no worries. Yeah. Okay, so starting from my standard form equation, A is negative 12, and x naught is 1, b is 6, and y naught is 2, c is 6, and z naught is 3. Okay. Now, to get this into general form, I'm going to distribute. So I have negative 12x plus 12 plus 6y minus 12 plus 6z minus 18. And then collecting all of my constant terms is going to be this. Plus 12 minus 18. There we go. And many of you may notice, since the right side of this equation is 0, I could just divide through everything by 6. And I could have written negative 2x plus y plus z minus 3 equals 0. But either way, I would give you full credit. But I just want you to know, you might see the simplified version on like a multiple choice exam, if that ever happens.
It's like taking another normal vector.
Yeah, exactly. Yeah, so this vector, negative 12, 6, 6, is normal to the plane, but the vector negative 2, 1, 1 would also be normal to the plane. And you can find a whole bunch of vectors normal to the plane just by multiplying or dividing. So this is, again, to remind the standard form, but what we were asked for our answer was general form. And so that is our general form. Okay. Now, two planes in 3D space. You can imagine two distinct planes. You've got two cases. Either those planes are going to be parallel and never intersect each other, just like if this tabletop is a plane in space and I hold this plane perfectly flat, then these will never intersect each other. Or they're going to intersect along a line. Right? Those are the two cases. And so that line we call a line of intersection. Along that line of intersection, the angle at which those two planes are going to intersect is going to be constant. And you can determine that angle of the planes, angle between the planes, just like you would if you take the normal vectors of the plane and you just calculate the angle between the normal vectors. So like right here, n1 and n2 are the normal vectors of plane number 1 and plane number 2. And you should already recognize that formula from just the angle between the vectors formula. So what does it mean if this dot product n1 dot n2 is equal to 0? What does that mean?
Perpendicular.
Yeah. That would mean the normal vectors are orthogonal. And if the normal vectors are orthogonal, that means the planes themselves are also orthogonal. Then what does it mean if n1 is just a scalar multiple of n2?
The same plane.
Yeah. So that would mean that your normal vectors are parallel to each other, which means that the planes are also parallel to each other. Yeah.
But not necessarily the same, right?
Yeah, they don't have to be the same plane.
Okay.
They could have the same normal vector and not be the same plane. They could just be parallel planes.
Okay, so we need another information like one point to determine if they're the same plane or not.
Yes. Mm-hmm. Okay. And then this last theorem says, whatever the line of intersection is between two planes, that line is going to be orthogonal to the normal vectors of both planes.
Is it correct to say perpendicular instead of normal? Is it just the same?
Yeah. Whenever I hear the word perpendicular, I think of like two-dimensional geometry. Like in a 2D plane, you can have vectors that are perpendicular or sides that are perpendicular. I usually just use the word orthogonal for higher dimensions, like 3-dimensional, 4-dimensional, and so on. But it's pretty much the same, pretty much the same vocabulary. Here's an example. For these two planes, so I have two different equations in general form that give me two different planes. We're first going to find the angle between them, and then we're going to find the parametric equations for their line of intersection. So, for this plane over here, if I want to find the normal vector, what is a normal vector?
1, -3, 1.
Perfect. So 1, -3, 1 is a normal vector just because those are the coefficients on my variables x, y, and z in the equation for the plane. And then over here, a normal vector could be yeah, 2, 3, -2, again, because those are just the coefficients on x, y, and z. So that's how you find normal vectors from the equation for a plane. If I want to find the angle between them, I'm going to use my dot product formula over norm in 1, norm in 2. Another way you can think about this dot product formula that is maybe it's longer to compute, but to me is like more satisfying, is I like to think of this formula as the angle between vectors is like if you just normalize the vectors first. Remember the little hat means it's a normalized vector, it's a unit vector. And so if you normalize them and then take the dot product, that's like a nice, it looks pretty. It's very short and simple. Anyways, n1 dot n2 would be 1 times 2, 2, plus -9 plus -2, so it would just be -9. The norm of n1 would be root 11, and the norm of n2 would be root 17.
equation, it had two lines on the initial part. Is that absolute value or am I missing something?
You're right, it is absolute value.
Okay.
Because whenever we talk about the angle between planes, it doesn't really make any sense to talk about negative, right? So like, if I say the angle between these planes is 30 degrees, I could also say the angle between the planes is negative 30 degrees, but like, who cares, you know? And so the absolute value is sort of like saying, oh, by the way, who cares? That doesn't need to be a negative 9. That can be a positive 9, and it doesn't really matter. Does that make sense? Okay.
Just making sure. 'Cause
Yeah. No, you're right. There was an absolute value there. So anyways, this is going to be, this angle is going to be the arc cosine of 9 over the square root of 11 times 17, which you could do in your calculator and you would eventually find, oops, that's not correct. There we go. That's how you would find the angle between these two planes. You just find the normal vectors and then you find the angle between the normal vectors, which we've done before. What I haven't done is I haven't found the parametric equations of their line of intersection. But remember that the line of intersection has to be orthogonal to both normal vectors. How do you find a vector that's orthogonal to the two normal vectors?
Cross product.
You take the cross product. The cross product is just a way to give you a vector that is orthogonal to two other vectors. And so you do n1 cross n2 to get a vector, and that's how you know the direction of the line of intersection. And then you also need a point along that line of intersection to fully describe the line. So to find a point on the line of intersection between the planes, it has to be a point xyz that satisfies both of those equations simultaneously. So you could solve a system of two equations simultaneously just by substitution or elimination or something like that. And we'll do that tomorrow. But we ran out of time today, so.
And since we have